Yeah. Okay, so welcome everybody. Today we are very happy to have Kansei Inamura from Oxford talking about non-invertible symmetries on a tensor product Hilbert space in 1 plus 1D. Take it away.
Thank you. So thank you for the introduction, and thank you for inviting me to give a talk. So today I'm going to talk about non-invertible symmetries in 1+D lattice models with a tensor product Hilbert space, or in other words, non-invertible symmetries in 1+D quantum spin chains. So this talk is based on my recent paper that I posted on arXiv this February. So So the main goal of this talk is to discuss general constraints on possible symmetry structures on a tensor product Hilbert space, in particular, non-invertible symmetry structures on a tensor product Hilbert space. And we know that there are many examples of non-invertible symmetries that can be realized on a tensor product Hilbert space, such as the Kramers-Warnier self-duality of the critical Ising model or the Repage symmetry of the finite group gauge theory in 1% dimensions, and so on. But nevertheless, there are also many examples of non-invertible symmetries whose realizations on a tensor product Hilbert space are not known yet. For example, the lattice realization of the Fibonacci fusion category symmetry on a tensor product Hilbert space is not known. So in this talk, I want to discuss which non-invertible symmetries can be realized in principle on a tensor product Hilbert space and which ones cannot. So the main question that I will address in this talk is the following. So the question is, which non-invertible symmetries can be or cannot be realized in 1+D lattice models with a tensor product Hilbert space? So throughout this talk, we will only consider 1+1 dimensional lattice models. So the space-time dimension is always 1+1. And I will make this question more precise later on. But before going into details, let me begin with a brief review of non-invertible symmetries.
Can I ask a quick question?
Sure.
I guess you also want to require that the symmetry acts locally in some sense, right?
Yes, yes.
But it's not super clear what's the meaning of that for non-invertible symmetries. Are you going to explain this?
Oh, in this talk, I will not specify the precise definition of symmetry operators. I just specify some physical assumptions on the symmetry operators, and I will explain the details later.
Okay, thank you.
So, anyway, let me begin with a brief review of non-invertible symmetries in order to give a motivation to consider this problem. So, and in particular, I wanted to start from symmetries in QFTs and then move on to the symmetries on the lattice. So let's begin with symmetries in QFTs. So, um, so as we know, the notion of global symmetry has been greatly generalized in the last decade, and in particular in relativistic QFTs, the symmetry operators or defects are generally defined by topological operators or defects. And one important consequence of this definition is that symmetry operators in QFTs can be non-invertible because topological operators can be non-invertible. And the symmetries generated by such non-invertible operators are called non-invertible symmetries. And by definition, these non-invertible symmetries cannot be described by groups in general, just because they are non-invertible. And instead, these symmetries are generally described by some sort of categories. So for example, in 1% dimensional QFTs, finite non-invertible symmetries are generally described by unitary fusion categories. And for this reason, these symmetries are called fusion category symmetries. And remarkably, it is known that any fusion category symmetry can be realized in some 1+1D QFTs. And indeed, there is a systematic construction of TQFTs with a given unitary fusion category symmetry. So any fusion category symmetry is realizable in continuum QFTs. So that's the situation in continuum. But how about the symmetries on the lattice? So on the lattice, the situation is different from the continuum. And one main difference between lattice models and continuum QFTs is that on the lattice, the state space is given by the tensor product of finite dimensional on-site Hilbert spaces. So if we denote this on-site Hilbert space by HO, then the state space on the entire lattice is given by the tensor product of capital N copies of HOs, where this capital N is the number of sites. So here I should mention that in this talk, I will not consider anyon chains unless otherwise stated. So the state space on the lattice always admits a tensor product decomposition. And also the on-site Hilbert space is always finite dimensional. So that's what I mean by lattice model in this talk. And due to this tensor product structure, the symmetry that can be realized on the lattice is highly constrained. And indeed, it was recently proven in a mathematical paper by Evans and Jones that a fusion category symmetry C in 1% dimensions can be realized on a tensor product Hilbert space if and only if it is integral. And here, our integral fusion category is a fusion category such that every object has an integral quantum dimension. So basic examples include the category of G-graded vector spaces with anomaly omega. So this is just an invertible symmetry, and rep-G symmetry, rep-G category, and Tamura-Megami categories based on some specific choice of abelian group, and so on and so forth. So there are many examples, but still, this is a very limited class of fusion categories. And there are many examples of fusion categories that are not integral. So this mathematical result by Evans and Jones implies that the symmetry on the lattice is highly constrained by this tensor product structure. But this is not the end of the story, and people also know that there are some examples of non-integral fusion category symmetries that can be realized in a slightly modified way on a tensor product Hilbert space. And a prototypical example of this kind of symmetry is the Kramers-Wanier self-duality of the critical Ising model. So let me go through this example and see what is happening. So first of all, in the continuum limit, or in other words, in the Ising CFT, this Kramers-Wanier symmetry is described by an non-integral fusion category, which is the Z2 Tambara-Megami category. So the fusion rule of the non-invertible Kramers-Wanier duality line is given by this equation. So here 1 is the identity line, and eta is the generator of the Z2 spin flip symmetry. And this fusion rule implies that the quantum dimension of the Kramers-Wanier duality line is given by the square root of 2, which is not an integer. So this is not an integral fusion category. And according to the result by Evans and Jones, it follows that this fusion category symmetry cannot be realized on a tensor product Hilbert space. But nevertheless, we know that the Kramers-Wanier self-duality is a symmetry of the critical Ising model on the lattice with a tensor product Hilbert space. So this might look a contradiction, but actually this is not a contradiction. So what is happening is that on the lattice, the fusion rules of this non-integral fusion category symmetry mix with the lattice translations as shown here. So if we fuse two copies of the Kramers-Wanier duality operators on the lattice, then we get 1 plus eta, but shifted by a lattice translation t. And due to this mixing with lattice translation, the Kramers-Wanier symmetry on the lattice is not quite a fusion category symmetry, but it's more like a fusion category symmetry up to lattice translation. So, and of course, the full mathematical structure of this symmetry is not a fusion category because this symmetry involves lattice translations. So precisely speaking, we should avoid calling this symmetry a fusion category symmetry. But in this talk, I will call this kind of symmetry fusion category symmetry that mixes with lattice translation, or fusion category symmetry up to lattice translation. And this fusion category symmetry up to lattice translation flows to a genuine fusion category symmetry in the continuum, which is in this case the Tamura-Megami category. And this continuum, fusion category symmetry in the continuum can be non-integral. So that's what is happening in this example. So this example motivates us to ask which kind of fusion category symmetries admit this sort of realization on the lattice. So the question is, which fusion category symmetries can be realized on a tensor product Hilbert space if we allow mixing with lattice translations. And here I should mention that this question was one of the open problems mentioned at the KITP program on generalized symmetries last year, and we can watch the video recording at this website. So anyway, we are interested in what kind of fusion category symmetries can be realized up to lattice translation on a tensor product Hilbert space. And slightly more generally, we can also consider non-invertible symmetries that mix with more general quantum cellular automata, QCAs, rather than just lattice translations. So as a slightly more general version of this question, we can ask which fusion category symmetries can be realized on the tensor product Hilbert space if we allow mixing with QCAs. And here QCA, or quantum cellular automaton, is defined as a locality preserving unitary. So it's a unitary operator that maps local operators to nearby local operators. And we impose a strict locality. And for example, the lattice translation by a finite number of sites is an example of a QCA because it clearly maps local operators to nearby local operators. But on the other hand, in this context, the reflection is not an example of a QCA because it maps local operators to local operators that are supported far away from the original position of the operators. So in our context, the lattice translation is a QCA, but the reflection is not. And in 1+ dimensions, it is known that any QCA is essentially a lattice translation up to finite depth circuits. Or more precisely speaking, when the dimension of the on-site Hilbert space is a prime, then any QCA is a lattice translation up to finite depth circuits. And when the dimension of the on-site Hilbert space is a composite of primes, then we are also allowed to do lattice translations for sub-Hilbert spaces of prime dimensions. And any QCA is a lattice translation of this kind up to finite depth circuits. And as I already mentioned, in this talk, I will only consider 1+ dimensional systems. So any QCA is essentially a lattice translation up to finite depth circuits. And so our question is, which fusion category symmetries can be realized up to QCAs on a tensor product Hilbert space?
I have a quick question. So when you mention QC in this context, do you always assume it has a non-trivial GNVW index?
No, it can have a trivial GNVW index.
Okay. All right, thanks.
Yeah. So we are interested in which fusion category symmetries can be realized up to QCAs on a tensor product Hilbert space. But this question is still a bit ambiguous because we haven't specified the precise meaning of fusion category symmetries up to QCAs. We haven't specified what we mean by fusion category symmetries up to QCAs in a precise sense. So to be more precise, in this talk, we consider the following more specific version of this question. So the question is the following. So first, we suppose that we have a finite set of symmetry operators on a tensor product Hilbert space. So these symmetry operators are labeled by some simple objects of a unitary fusion category C. So this is just a finite set of symmetry operators. And then we suppose that these symmetry operators obey the fusion rules of this unitary fusion category C up to QCAs. So here the summation is taken over all possible fusion channels of X tensor Y, including fusion multiplicities, and UXYZ is an arbitrary QCA. And then the question is, which fusion category can C be? For example, can C be the Fibonacci fusion category, or can C be the Hagelab fusion category, etc. So here I want to emphasize that in this talk, I will only care about the fusion rules. In particular, I will not care about F symbols. So we will only require that the fusion rules of the symmetry operators agree with those of a unitary fusion category C up to QCAs, and then we ask which fusion category C can be. That's the question. Is there any questions so far? Okay. So regarding this question, there is a recent conjecture which was originally proposed in the KITP program.
Sorry, I have one
That
quick question.
Mhm.
I have one quick question. Is the QCA by itself allowed to be non-invertible, or do you want the QCA to be unitary? The QCA.
QCA is always invertible.
Okay, so there is no possible generalization of QCAs that allows them to be non-invertible. Because I can imagine here um, that you could have some modification in which also the that the operator that you are allowing to enter here are also non-invertible somehow. But they
Yes,
all, yeah.
DX can be non-invertible.
Yeah, I mean the operators that somehow are supposed to flow to the trivial operators in the continuum.
Um, well, I do not assume that UXYZ flows a trivial operator in the continuum. Or in this talk, I will not consider continuum limit. I'm always considering lattice models.
But I guess the starting point is some given fusion category, and and in principle, you are allowing modification of that fusion category that are only visible on the lattice, right?
Right.
So somehow there should be a concept that the U's are all operators flowing to the trivial operator in the continuum limit. Yeah, okay. I'm just wondering whether there can be more general situations, but okay. It doesn't matter.
Yeah. Sorry. Yeah.
Thank
Yeah.
you.
In this talk, I will not consider any continuum limit.
Okay, thank you.
I have one more question. So for the icing case, the U's are like the same. It's like an overall factor of T. But here, do you allow this U to actually depend on, say, like different fusion outcomes can be different?
Yes, I allow that you can depend on Z.
Okay, thanks.
So regarding this conjecture, regarding this question, there is a conjecture which was proposed in the KITP program that I mentioned before.
Sorry. Step back to the previous. Thank you. Is there a sense in which this QCA can be thought of as being normal so that you can take the quotient by it? I believe it's related to the previous question about the continuum limit, but I try to think how to formulate it on the lattice without taking the limit. So the question is really, is that what underlies it? So that there is a sensible category after you take a quotient by the QCA.
I haven't thought about taking the quotient by QCAs. Yeah,
Well, that's what you did before.
that's what you do.
Okay.
Yes, if we want to consider the continuum limit, then we should have some such kind of notion.
Right, but since you replied earlier to the previous question that you're not discussing the continuum limit, I'm asking the same question directly on the lattice by asking whether there is a sense in which you can take a quotient by this QCA. I believe that's what the previous question was about, was it?
Yes, yes. Essentially, yes. I didn't think about taking the quotient, but that's essentially what I had in mind by asking about the continuum limit. That somehow in the continuum limit, this U's should disappear. So there should be a sense in which this is just taking the quotient.
Right, but you can take the quotient already on the lattice. The quotient might not, in general, will not act well, and that's why we don't discuss it. But at the level of this category, I wonder whether this is a sensible way to reformulate what Andrea was saying. But if you didn't think about it, that's fine. Just keep going.
Yeah, thank you. I haven't thought about this. Sorry. So there's a conjecture, and so this conjecture was clearly stated in a talk by Nat Tantegasarakan at the Newton Institute in Cambridge. And this conjecture states that even if we allow mixing with QCAs, only weakly integral fusion category symmetries can be realized on a tensor product Hilbert space. And I will call this conjecture a weakly integral conjecture. So here, a weakly integral fusion category is a fusion category such that the quantum dimension of every simple object is the square root of an integer. So for example, every integral fusion category is weakly integral because every integer is the square root of an integer. And also the Tamaragami category, the Z2 Tamaragami category is weakly integral because the quantum dimension of the Kramers-Swann duality line is given by the square root of it. But on the other hand, the Fibonacci fusion category is not weakly integral because the quantum dimension of its non-invertible object is the golden ratio, which is not the square root of integer. So if this weakly integral conjecture is true, then it follows that the Fibonacci fusion category cannot be realized on a tensor product Hilbert space, even if we allow mixing with QCAs. And in this talk, I will give a conditional proof of this conjecture based on some physical assumptions on the symmetry operators. So my approach is that I will first make some physical assumptions on the symmetry operators without specifying precise definition of the symmetry operators. And based on these assumptions, I will give a conditional proof of the weakly integral conjecture. So precise definition of the symmetry operator does not matter in this talk as long as my physical assumptions are satisfied. So I will not specify the precise definition. I will only use the physical assumptions. And before moving on, I should also mention that more evidence of this conjecture was recently provided by these papers by Liu, Chatterjee, Tantevasarakan, and also Jones and Yan. So here is the outline of the rest of this talk. So first, I will specify the physical assumptions on the symmetry operators, and our discussion in the rest of this talk will be based only on these physical assumptions. And then I will introduce some key quantities, which I will call lattice quantum dimension and the index of non-invertible symmetry operators. And after that, I will present my main results on which fusion category symmetries can be or cannot be realized on the tensor product Hilbert space up to QCAs. And I will also sketch out a proof of these results. And finally, I will give a brief comment on the case of the anion chains. And of course, in the case of the anion chains, the state space does not admit a tensor product decomposition. So the weakly integral conjecture does not apply to this case from the beginning, but I will try to clarify which part of the proof breaks down in the case of the anion chain. So let me begin with the physical assumptions. So basically, my physical assumption is that for every symmetry operator, there exists a corresponding defect Hilbert spaces that satisfy appropriate conditions. So more specifically, we assume that for every symmetry operator D, there exists a pair of defect Hilbert spaces denoted by HDL and HDR that satisfy the properties that I will list below. So here HDL is a defect Hilbert space in the presence of a defect oriented upwards, and HDR is a defect Hilbert space in the presence of a defect oriented downwards. And by slight abuse of notation, I will denote the defect and the corresponding symmetry operator by the same letter, which is D here. And my assumption is that these defect Hilbert spaces satisfy the following 4 properties. So the first assumption is that these defect Hilbert spaces are obtained by local modifications of the Hilbert space without a defect. So this means that if the original Hilbert space without a defect is given by the tensor product of the on-site Hilbert spaces like this, then the defect Hilbert space HDL is obtained by first removing some finite number of physical sites, denoted by NL, around the defect, and then adding a new physical degrees of freedom, capital L, at the position of the defect. So here this capital L is a finite dimensional Hilbert space that we put at the position of the defect, and small nl is a non-negative integer, which is the number of sites that we remove around the defect. And similarly, HDR is obtained by removing a finite number of physical sites nr around the defect, and then adding a new physical degrees freedom r at the position of the defect. So here both capital L and capital R finite dimensional Hilbert spaces, and small nl and small nr non-negative integers. And we assume that all of these quantities are independent of the system size, so that this modification is completely localized around the defect. So that's what I mean by local modifications. And also, I implicitly assume that these defect Hilbert spaces are independent of the position of the defect up to isomorphism. So this is my first assumption. And
Sorry, quick question. Is there a canonical isomorphism between HLD and HRD?
Isomorphism between HL and HR?
Yes.
No, there is no isomorphism.
I
For
don't think
example,
it's just related by orientation reversal of D.
yeah. There is some relation between HLD and HRD dagger, and that's one of my other assumptions.
Oh, I see. I see.
Yeah, I will get to there. So that's my first assumption, and my second assumption is that the defect Hilbert spaces are compatible with the fusion of the symmetry operators. So namely, we assume that the defect Hilbert space corresponding to the composite symmetry operator, dx times dy, is isomorphic to the defect Hilbert space in the presence of two separate defects corresponding to dx and dy. And here the right-hand side is just obtained by removing some finite number of physical size around these defects, then adding new physical degrees of freedom at these positions. So more specifically, if the defects are oriented upwards, then this right-hand side is obtained by first removing NLX size around the defect dx and NLY size around the defect dy, and then adding new physical degrees of freedom, capital Lx and capital Ly, at the position of the defects dx and dy. And my assumption is that the defect Hilbert space obtained in this way is isomorphic to the defect Hilbert space corresponding to a composite symmetry operator dx times dy. And we also assume a similar isomorphism for the right version of this defect Hilbert space. Okay, so this is my second assumption. And the third assumption is that these defect Hilbert spaces are also compatible with the summation of the symmetry operators. So, namely, we assume that the defect Hilbert space corresponding to dx plus dy is isomorphic to the direct sum of the defect Hilbert spaces corresponding to dx and dy. So more specifically, we assume that HL dx plus dy is isomorphic to the direct sum of HL dx and HL dy, and HR dx plus dy is isomorphic to the direct sum of HR dx and HR dy. And my last assumption is that the defect Hilbert spaces are also compatible with the Hermitian conjugation of the symmetry operators. So we assume that the defect Hilbert space corresponding to D dagger is isomorphic to the defect Hilbert space corresponding to D, but with the opposite orientation of the defect. So more specifically, we assume that HL D dagger is isomorphic to HRD, and HRD dagger is isomorphic to HLD. So this means that taking the Hermitian conjugation of the symmetry operator amounts to exchanging left and right, or flipping the orientation of the defect. So these are my physical assumptions. So my physical assumption is that for each symmetry operator, there exists a pair of defect Hilbert spaces, and these defect Hilbert spaces are obtained by local modifications and are compatible with the fusion, summation, and Hermitian conjugation of the symmetry operators. So that's my physical assumption. And based on these assumptions, we can now discuss which fusion category symmetries can be realized up to QCAs on a tensor product Hilbert space. But before moving on to the main results, I want to first introduce some key quantities, which I will use in the later discussions. And we will call these quantities lattice quantum dimension and index. So in order to define these quantities, let me first define the left dimension and the right dimension of the symmetry operators. And the definition is as follows. So the left dimension of a symmetry operator D is defined by the ratio of the dimension of the defect Hilbert space, HDL, and the dimension of the Hilbert space without a defect. And similarly, the right dimension of the symmetry operator D is defined by the dimension of HDR divided by the dimension of H. So by definition, these quantities are positive rational numbers because they are just ratios of positive integers. And this fact will play a crucial role in the later proof. So these are positive rational numbers. And furthermore, these quantities are independent of the system size because HDL and HDR are obtained by local modifications. And indeed, we can write down these left dimension and right dimension in terms of purely local quantities, as shown here. And this expression is manifestly independent of the system size. So the left dimension and the right dimensions are positive rational numbers that are independent of the system size. And also I'd like to mention that these quantities were originally introduced in the paper by Seiberg, Seifenasri-Schall, and in their paper, these quantities were called lattice quantum dimensions. But in this talk, I will reserve this name, lattice quantum dimension, for another quantity that I will introduce in the next slide. So these are the definition of the left and right dimensions. And then by using this left and right dimensions, we can now define the lattice quantum dimension and the index in the following way. So the lattice quantum dimension of a symmetry operator D is defined by the square root of the product of the left dimension and the right dimension. And on the other hand, the index of symmetry operator D is defined by the square root of the ratio of the left dimension and the right dimension. So by definition, these quantities are the square roots of positive rational numbers. And in particular, when D is a QCA, when the symmetry operator D is a QCA, then one can show that the lattice quantum dimension is always equal to 1. And this follows from my physical assumptions. And indeed, due to the assumption that the defect Hilbert spaces are compatible with Hermitian conjugation, it immediately follows that the left dimension of D is equal to the right dimension of D dagger. But when D is a QCA, D dagger is equal to D inverse. So this middle quantity is the right dimension of D inverse. And furthermore, due to the assumption that the defect Hilbert spaces are compatible with the fusion, it follows that the right dimension is multiplicative under the composition of the symmetry operator. So in particular, it means that the right dimension of D inverse is equal to the inverse of the right dimension of D. So we find that when D is a QCA, then the left dimension of D is equal to the inverse of the right dimension of D. And by plugging this equation into the definition of the lattice quantum dimension, we find that the lattice quantum dimension of every QCA is equal to 1. So this shows the first breakpoint. And furthermore, one can also show that when D is a QCA, the index defined here agrees with the so-called GNVW index. So in that sense, our index can be regarded as a generalization of the GNVW index to the case of non-invertible symmetries. And now based on this setup, we can discuss which fusion category symmetries can be realized up to QCAs on a tensor product Hilbert space. So let me move on to the main result.
Sorry, I have one confusion. I probably just didn't completely get the definitions, but suppose the dagger is equal to D. I didn't really appreciate how the left Hilbert space and the right Hilbert space are different.
Did you say suppose what?
The D dagger is equal to D.
Uh-huh.
So my intuition is just so that if the dagger is equal to D, orienting the defect upwards or downwards, just exchange D and the dagger. But if the D and the dagger are the same, the twisted Hilbert space should be the same. But probably what you're defining is not what I have in mind as the twisted Hilbert space. So you didn't completely get the definition, probably.
I guess when D is equal to D dagger, then I guess it cannot have a non-trivial GNVW index.
Okay.
And, yeah.
Okay.
And in that case, the left the HL and HR becomes isomorphic to each other.
Okay. So my intuition was correct. Okay.
Yeah.
Okay. So for easing, for instance, it's trivial.
You mean C2 symmetry of the idea?
Yes. Yes.
Yes, that's right.
Okay. Thank you.
So let me move on to the main results. And the main result consists of two statements. So I have two statements. And the first statement is about non-invertible symmetries that do not mix with lattice translations or more general QCAs. And the second statement is about non-invertible symmetries that do mix with QCAs. So let me begin with the first statement. So the statement is as follows. So first, we suppose that we have a finite set of symmetry operators on a tensor product Hilbert space. And then we suppose that these symmetry operators obey the fusion rules of a unitary fusion category C exactly on the lattice. And then based on the physical assumptions mentioned before, we can show that this fusion category C must be integral. So this result shows that the fusion category symmetry C realized exactly on the lattice on a tensor product Hilbert space must be integral. And in particular, this result reproduces the mathematical result of Evans and Jones. More precisely speaking, in the paper by Evans and Jones, they also show the converse, which means that every integral fusion category symmetry can indeed be realized on a tensor product Hilbert space. But on the other hand, this result, my result, doesn't say anything about which integral fusion category symmetries can indeed be realized on a tensor product Hilbert space. So my result only shows that if a fusion category symmetry is realized on a tensor product Hilbert space, then it's integral. But I didn't say anything. I didn't say anything about converse. So in that sense, this result is weaker than the result of Evans and Jones. But one advantage of this physical approach is that we can easily generalize this statement to the case where the symmetries involve lattice translations or more general QCAs. So that's the content of my next statement. So the second statement is the following. So again, we suppose that we have a finite set of symmetry operators on a tensor product Hilbert space. And then we suppose that these symmetry operators obey the fusion rules of a unitary fusion category symmetry C up to QCA. So here UXYZ is an arbitrary QCA. And then based on the same physical assumptions, we can show that if all summands on the right-hand side of this equation have the same index, then the fusion category C must be weakly integral. So this result shows that as long as all the fusion channels have the same index, then the fusion category symmetry realized on a tensor product Hilbert space must be weakly integral, even if we allow mixing with QCAs. So in particular, this result is consistent with the weakly integral conjecture that I mentioned before. Or more specifically, this result shows the weakly integral conjecture with an additional condition that all the fusion channels have the same index. Okay. So in the rest of this talk, I will sketch out a proof of this statement. But before moving on to the proof, I have several remarks. So the first remark is that the condition that all the fusion channels of dx times dy have the same index is equivalent to the condition that the index of every fusion channel is given by the product of the indices of dx and dy. So it is clear that if this equation is satisfied, then all the fusion channels of dx times dy have the same index, which is just the right-hand side of this equation. But the non-trivial thing is that we can also show the converse, and this can be checked by direct computation. So this is the first remark. And the second remark is that when both dx and dy are QCAs, then this equality of index has already been established in the literature, and this is known as the index theory of QCAs. So in the case where dx and dy are QCAs, then this condition, this equation is not an additional condition. This is already established. But on the other hand, for more general non-invertible symmetries, the index theory has not been established yet, mainly because the precise definition of non-invertible symmetry operators on the lattice is not available in the literature. So in particular, this equality of index has not been verified in a full generality. So this is still open for general non-invertible symmetry operators. But once the index theory of non-invertible symmetries is established, and once this equality of index is proven in full generality, then our result implies that the weakly integral conjecture holds. So in other words, if we want to show the weakly integral conjecture, then what we should do is to establish the index theory of non-invertible symmetries. So that's one implication of this result. Okay. Are there any questions about this result? Okay, so in the remaining time, I want to sketch out a proof of this result. So to begin with, let me first show the following properties of the left dimension, because I will use this property in the later proof. And the case of the right dimension is similar, so here I will focus only on the case of the left dimension. So the first property that we can show is the multiplicativity, which means that the left dimension of dx times dy is equal to the product of the left dimensions of dx and dy. And this multiplicativity follows from the assumption that the defect Hilbert spaces are compatible with the fusion of the symmetry operators. So here we recall that this assumption can be written in the form of an equation like this. So here the left-hand side is the defect Hilbert space corresponding to a single composite operator, and the right-hand side is the defect Hilbert space in the presence of two separate defects. And based on this expression, we can easily compute the left dimension of dx times dy like this, and we can easily see that this equation, this quantity is equal to the product of the left dimension of dx and the left dimension of dy. So this shows the multiplicativity. And another property that we can show is the additivity, which means that the left dimension of dx plus dy is equal to the sum of the left dimensions of dx and dy. And this is an immediate consequence of the assumption that the defect Hilbert spaces are compatible with the summation of the symmetry operators. So what we showed here is that the left dimension is multiplicative and additive, and we can also show the same properties for the right dimension. And based on this multiplicativity and additivity, we can now prove the main statements. So let me begin with the proof of the first statement, which I copied here. So what we want to show is that if we have a finite set of symmetry operators on a tensor product Hilbert space that obey the fusion rules of C exactly on the lattice, then C must be integral. And in order to show this statement, we first notice that the left dimension and the right dimensions are one-dimensional representations of the fusion rules of the symmetry operators. This is because the left dimension and the right dimension are multiplicative and additive. So in particular, when the symmetry operators obey the fusion rules of C, then the left dimension and the right dimension are one-dimensional representations of the fusion rules of C. So they satisfy these equations. And furthermore, by definition, these are positive one-dimensional representations. But on the other hand, it is known that the positive one-dimensional representation of the fusion rules of a unitary fusion category C is uniquely given by the quantum dimension. So this means that the left dimension and the right dimension are actually equal to the quantum dimension. And since the left dimension and the right dimension are rational numbers by definition, this equation implies that the quantum dimension is also a rational number. On the other hand, it is also known that the quantum dimension of any object of a fusion category is an algebraic integer. So by combining this second bullet point and third bullet point, we find that the quantum dimension is a rational algebraic integer. But it is also known that any rational algebraic integer is an integer. So this means that the quantum dimension of x is an integer for every simple object x in C. So this concludes a proof of the first statement. And here I want to emphasize that the crucial part of this proof is that the left dimension and the right dimension are rational one-dimensional representations of the fusion rules. And this property will break down in the case of the anion chains, as we will discuss later. So this is where the tensor product structure comes in. And similarly, we can also show the second statement, which I copied here. So what we want to show is that if we have a finite set of symmetry operators on a tensor product Hilbert space that obey the fusion rules of C up to QCAs, and if all the fusion channels have the same index, then C must be weakly integral. So we want to show this statement. And in order to show this statement, we again use the fact that the left dimension and the right dimension are one-dimensional representations of the fusion rules. So, but this time, these left dimension and right dimension are not one-dimensional representations of the fusion rules of C because we have an additional factor of QCA on the right-hand side. And here the left dimension of UXYZ and the right dimension of UXYZ are not necessarily one. So this is not the one-dimensional representation of the fusion rules of C. But anyways, the left dimension and the right dimension satisfies these equations. And by using these equations, we can also show that if all the fusion channels have the same index, then the lattice quantum dimension is also a one-dimensional representation of the fusion rules. So what we can show is that if the index of the fusion channel Z is equal to the index of another fusion channel W for any pair of Z and W, then the lattice quantum dimension satisfies this equation. But again, we have an additional factor of QCA, UXIZ on the right-hand side. So this does not look like a one-dimensional representation of the fusion rules of C. But an important point is that the lattice quantum dimension of any QCA is equal to 1. So this means that we can simply drop this additional factor on the right-hand side. And therefore, as a result, we end up with a one-dimensional representation of the fusion rules of C. So what we found here is that if all the fusion channels have the same index, then the lattice quantum dimension becomes a one-dimensional representation of the fusion rules of C. And furthermore, by definition, this is a positive one-dimensional representation. And now we can run the same argument as before. So again, we use the fact that the positive one-dimensional representation of the fusion rules is uniquely given by the quantum dimension, which means that the lattice quantum dimension is actually equal to the quantum dimension. And since the lattice quantum dimension squared is a rational number, this equation implies that the quantum dimension squared is also a rational number. On the other hand, since the quantum dimension is an algebraic integer, its squared is also algebraic integer. So by combining the second bullet point and third bullet point, we find that the quantum dimension squared is a rational algebraic integer. But again, any rational algebraic integer is an integer. So it follows that the quantum dimension squared is an integer. Or in other words, the quantum dimension is the square root of an integer, which means that the fusion category C is weakly integral. So this concludes the proof. So finally, I want to discuss as a case of the anion chains, and I want to clarify why this proof does not apply to the case of the anion chains. So to this end, let me first recall the definition of the anion chains. So the anion chain is a 1% dimensional lattice model constructed from a fusion category C, and its state space is spanned by the fusion diagrams of this form. So here rho is a fixed object, which is not a dynamical variable, but this choice of rho determines what kind of configurations of dynamical variables are allowed on this lattice. And in particular, this state space does not admit a tensor product decomposition. And as is well known, the anion chain model obtained from a fusion category C has an exact fusion category symmetry. And here by an exact fusion category symmetry, I mean the fusion category symmetry whose fusion rules do not mix with lattice translations. And since the state space does not admit a tensor product decomposition, our results do not apply to this case, obviously, but one may wonder which part of the proof goes wrong in this case. So, and the answer is that in the case of the anion chain, the left dimension and the right dimension are no longer rational one-dimensional representations of the fusion rules. And that's why our proof breaks down in this case. So in order to see this point, let us consider the the defect Hilbert space of the anion chain. So the defect Hilbert space of the anion chain is spanned by the fusion diagrams of this form in the presence of an additional vertical line labeled by some object x. And this is a topological line. And here the capital A and the capital B are fixed objects which specify the boundary conditions of this chain. But the choice of the boundary condition is not super important as long as they are sufficiently generic. And then the left dimension of the symmetry operator dx is defined by the ratio of the dimension of the defect Hilbert space and the dimension of the Hilbert space without a defect. And by definition, this quantity is rational, but it turns out that this is not a one-dimensional representation of the fusion rules. And even worse, this quantity depends on the system size n. So this is not a good number. And in order to obtain a better quantity, we can think of taking the limit where the system size goes to infinity. And in this limit, we can show that the left dimension agrees with the quantum dimension. So in particular, it is a one-dimensional representation of the fusion rules. But this is no longer rational in general, because we have taken the limit of a sequence of rational numbers. So the punchline is that in the case of the anion chains, the left dimension cannot be rational and one-dimensional representation of the fusion rules at the same time. And that's why our proof breaks down. And this is completely consistent with the fact that anion chains can realize any fusion category symmetries without mixing with lattice translations. So I think it's a bit earlier than schedules, but in summary, in this talk, we discussed which fusion category symmetries can be or cannot be realized on a tensor product Hilbert space. And under some physical assumptions, we showed that if a fusion category symmetry C is realized without mixing with QCAs, then it must be integral. And in particular, this result reproduces a mathematical result of Evans and Jones. And furthermore, under the same physical assumptions, we also showed that if a fusion category symmetry C is realized by mixing with QCAs, then C must be weakly integral, assuming that all the fusion channels have the same index. So this result supports the weakly integral conjecture by Tantiva-Sarakan. And in particular, this result suggests that if we want to show the weakly integral conjecture, then all we have to do is to establish the index theory of non-invertible symmetries. And as a final comment, I want to mention that the index theory of non-invertible symmetry seems to be currently under development. And this was mentioned in a recent talk by Saif Nasri, and we can watch the video recording here. So I hope this weakly integral conjecture will be settled down in the near future. So with that, I think I can stop here. So thank you for your attention.
Thanks a lot, Kansei, for this very nice talk. Are there any questions? Maybe I can start with one question. So suppose I start with one given fusion category. Is there you didn't discuss whether there are conditions on these QCAs that you introduce in the fusion rule, but I guess they must be consistent somehow with the associativity of the fusion category, so it cannot be completely arbitrary. Is there a way of starting from a fusion category, classify what are the possible extensions by QCAs that you can have?
No, at least I don't know how to classify such an extension.
Mm-hmm. For instance, for the easing fusion category, the extension by just adding t that multiplies 1 plus eta, do you think is the only possible one?
I
didn't think about it, but
yeah, I think there should be some constraint on the index of possible extension, possible QCA that we can put as u, x, y, z. So, and I think in the case of Ising fusion category. Yeah, sorry, I don't know. I don't have a concrete answer right now.
Okay, thank you.
Can we just follow up on this question? So how does because the condition is that the index on the left is the same as the index on the right for this to actually be possible. So the index of the x times y needs to be the same as the sum over the u x, y, z. How does the index behave with respect to multiplication and summation? Probably not very well at all. So in fact, you can't even break this down to each of the terms being of the same, having the same index or something, right?
Yes,
If you go back to this expression that you had.
Yeah. Yes, my expectation is that if we fuse two symmetry operators dx times dy and decompose it into indecomposable ones, then my expectation is that the index of each fusion channel must be given by this
I see,
product.
for all z. So in fact, you're saying this is linear, and each of the terms needs to be set. So then basically, you could still have freedom of having dz uz xy be different depending on z. I think
Right.
Ray's question was, is there actually an example where, the product is invariant, but you get different UCAs multiplying?
Yeah.
Like an example where you have translation in some channel and no translation in other channel, or T-square in other channel.
In fact, is there any other example apart from the Ising one?
Yeah, the only examples that I know is a kind of straightforward generalization of the Ising example.
The TY example.
Right. Yeah. I don't know any example where I
Related question is, so assume we know the fusion rule of the fusion of the fusion category together with these QCAs, and we know all the indices, the GMVW indices of the QCAs. Can we calculate all the indices of the objects of the fusion category?
Oh, do you assume that we know the fusion rules like this, and you know the index of uxyz, and you want to know the index of dx?
Yeah.
For all x. No, sorry, I don't know. Yeah, I don't know, sorry.
Any other question? I have a very quick one. You never showed the fusion coefficients, but I guess they were just like implicit when you were writing all the sums. Are you are you also allowing to have non-trivial fusion coefficients different from one?
Yes, I allow the non-trivial fusion coefficients.
Okay.
It's just implicit in this expression.
Okay. Any final question? So if not, thanks again for this very nice talk.